In this video we're going to work with two very important consequences of the monotone convergence theorem. If you haven't already, I recommend you first watch the monotone convergence theorem, and if you can, the previous video in which we used the monotone convergence theorem to solve an exercise from Follen's book. That exercise is going to be useful for the first of these two consequences. Now, before we start with the video, let me remind you that you can support the channel on a few different ways. You can use Ko-fi to make small donations or get access to exclusive content with Ko-fi memberships. If in addition to that content you want to get some merchandise, then you can use Patreon. Patreon will give you t-shirts, mugs, hoodies and many more things. But if all you want is the merchandise, then you can go directly to our store to buy the things individually. Well, that's enough for an intro. Let's dive right into this video. We will first prove that if f is a non-negative measurable function, then the integral of f is 0 if and only if f is 0 mu almost everywhere. That means that f is going to be 0 in every point except on a set of measure 0. And the second one says that if we have a sequence of non-negative measurable functions that increase to f almost everywhere, then we have basically the consequence of the monotone convergence theorem. So this is like an almost everywhere monotone convergence theorem. So it's weakening the monotone convergence theorem to something that's actually easier to get, because we will usually not have that two functions are equal everywhere, or that one sequence is increasing for every point to another. Instead, in measure theory, we usually have things like this, conditions that are only valid almost everywhere. Well, good news, we can still use monotone convergence theorem in this case. Let's start with the first one. So we have f, non-negative measurable function. Well, let's assume first that f is a simple function. If you saw our video on simple functions, then you know that usually we're going to prove things for simple functions and then adapt them for more general non-negative measurable functions. So if f is simple, let's say that f is of the form the sum of an times chi of en for some sets en that are measurable, and an, because the function is non-negative, then an will all be greater than or equal to 0. The integral of f, because it's simple, just using the definition, is going to be the sum of an times the measure of the sets en. And now, well, this integral is going to be 0 if and only if this sum is 0. And this sum will be 0 even only if all the terms are 0. That is, an equals 0 or the measure of en is 0. And these things will be satisfied if and only if the function itself is 0. Okay, so we have what we wanted to prove for simple functions. Now let's see what happens if f is not simple. Well, as I said, we're going to use simple functions to try and approximate the integral of f. So we can just let phi be a simple function such that it's between 0 and f. Well, we have to prove an if and only if. So let's start by saying what happens if f is 0 almost everywhere. In this situation, I forgot the almost everywhere, and that comes when this condition is satisfied instead of this one, but it's still trivial. So now if f is 0 almost everywhere, because phi is between 0 and f, well, this immediately implies that phi has to be 0 almost everywhere. But phi is a simple function, and we just proved that simple functions satisfy this. So if phi is 0 almost everywhere, then the integral of phi will be 0. This implies the integral of phi 0. Okay, so every time we grab a function between 0 and f, if the function f is 0, the integral of phi is 0. Well, what does this say about the integral of f? If you remember from our video on integration, we know that this integral is equal to the supremum of over all the phi's that are simple functions below f of the integral of phi. But we just said that each of these integrals was going to be 0. So this is 0. Perfect. We have one of the implications. Now we have to prove the other one. What happens now if the integral of f is 0? In the video about solving exercise 12, we thought we could write the set of all the points in the space where the function is strictly positive as the union over all the natural numbers n of the set of the points where the function is greater than 1 over n. What we want to do is show that this set has measure 0, because then the only option that we will have for f is that it's going to be 0 almost everywhere. Well, let's suppose by contradiction that f is not 0 almost everywhere. If it's not 0 almost everywhere, then there will exist some n large enough such that the measure of this set, let me call these sets En, so the measure of En will be positive, will be not 0, because f is not 0 almost everywhere. And now we will use the same trick that we used in the exercise, and we say, well, in this set En, f is greater than 1 over n. Because this happens in the set En, then we multiply by the characteristic, and then this is a valid inequality. Now I'm going to go faster because we already did this before, but I can just integrate. This will give me the integral over En of f, and this will give me the measure of En over n. But since the integral of f is 0, then in particular the integral over En of f will also be 0. So mu of En is going to be less than or equal to 0, right? Because I can multiply by n times 0 gives me 0. And so the measure of En is 0. But we said here that it was positive, and we are obtaining that it's 0. Contradiction. And this implies that f has to be 0 almost everywhere, because that is what we were assuming in this part here. Okay, great. So now we have proven the first of these two consequences. If we have a non-negative measurable function, the integral is 0 if and only if the function is 0 almost everywhere. Well, now let's prove the second part. Now we will have a sequence of non-negative measurable functions that grow to f almost everywhere. And we have to prove basically the monotone convergence theorem. What this means is that fn grows to f on some set E such that the measure of E complement is 0. So for every x in this set E we have the convergence, but all the other points have measure 0. So this means that we can work directly on the set E and everything will work as normal because we have on E conversions everywhere. So now let's see how we can translate this into the integrals. We want to start with the integral of f. But the integral of f on the entire space is the same as the integral on E plus the integral on E complement. Since the measure of E complement is 0, then this integral will also be 0. And so that leaves us only with the integral of f d mu. But good news, on E we have this. So for this integral we have the conversions everywhere of the sequences that are increasing, so we can just use the monotone convergence theorem and pull the limit out of the integral, as long as we are still integrating on this set E. But now it won't affect if I just add 0, so I can just add the integral on E complement of this sequence, because again this integral is just 0, and I can just put these two integrals together and say, well, the integral over E plus the integral over E complement, that is simply the integral over the entire space. And that is it. We have then monotone convergence theorem for conversions almost everywhere. That is weakening the monotone convergence theorem for something that's easier to obtain.